So, good morning.
Good morning.
We are going to continue from where we left last time, and now we are going to look at a line that has already been turned on. Okay, and then we either connect a load to it or we switch it off. That is, we call it an already charged in a line. So, any disturbance or change in a transmission line circuit will always start truncations along the line, even when there are no external excitations, as long as the initial voltages and currents exist on that line. So an example here is that a lossless air line or air dielectric open circuited line of resistive characteristic impedance Z0 and length L is initially charged to a voltage V0. So at t equal to 0, the line is then connected to a resistance R, and we are supposed to determine the voltage across the resistor and the current through it as a function of time. And we are told to assume that R is exactly equal to the characteristic impedance of the line. And therefore we expect no reflections. So what we can do is that we can always use superposition to try and solve this problem. And what we have is that this is the actual problem statement. The line is charged to a voltage V0, and at a time T0, T equal to 0, it's connected to a resistor R. And we want to see what happens. So what we are saying is that we can always change this value to show that we have two, this should be opposing that. I'll change that one for you. So what we are saying is that we can connect two voltages that are opposing so that we still get a zero voltage on the line, and then we connect it to this line, which is initially uncharged. It doesn't have any charge. So the first thing that happens is that we can separate this into two. That is, we have one a V0, okay, only the voltage V0 alone, and then we can add that to a line that is not charged, so to speak. So, so remember that this one is actually connected opposite to this one, so that we have zero voltage. We are just adding this one, just like the way you in circuit theory, you are told to add a null operator or a null element to try and solve the problems. So, since the voltage across R is initially zero, no current will flow through the resistor, and we can model the situation as shown in B, which can be redrawn as in C and D, which we have just shown here. That is C and D by the redrawing, where we are now using superposition. So the line is assumed to be uncharged with an initial charge represented by a voltage source. So when the switch is closed, a wave of amplitude V1 plus is sent down the line in the positive Z direction with an amplitude V1 plus equal to the minus of Z0 by Z0 plus R multiplied by V0. That is, we are using this particular equation here. So at t equal to L by V, that is the time of flight, this wave will arrive at the open circuit, having lowered the voltage everywhere on that line to a value V0 by 2. Because it had a value of V0, now the V1 plus will go, since it's negative, it will go discharging the line up to a value of V0 by 2. And the reflected wave of V1 minus is then sent back with a reflection coefficient of unity to the sending end, where the V1 minus is going to be given by gamma V1 plus, and that is multiplying what the value of V1 plus is, because gamma is going to be equal to unity because the terminating resistance or the terminating load is an open circuit. It will arrive at the sending end at a time t equal to 2L by V, that is the round trip time of flight, and lowers the line voltage to 0. And the current through the resistor will therefore be given by IR equal to the minus of I1, where I1 is, of course, the sending or the positive going current amplitude, which is V1 plus divided by Z0. And we can see that this is going to be just minus V0 by 2Z0. And this is during the time when the wave is moving in the positive Z direction, that is between 0 t less than 0 and the L over V, that is one way time of flight. So at t equal to L by V, the current will reach the open circuit and it will be reflected. And because it's being reflected, for the current, the line current to be 0 at the open circuit, then we must see that the current of the opposite going or the reverse moving or the reflected current wave must change sign, so that when we add I1 plus I1 minus, we get a 0 at that line at the position of the termination. And therefore we can see that I1 minus must be the negative of I1 plus, which we get as V0 by 2 Z0. And this will arrive at the sending end at a time t equal to 2L by V. And it will have reduced both I1 and IR to 0. And since R is equal to Z0, we expect no further reflections to take place, and the transient will then end. This circuit is useful as a pulse generator with a pulse duration adjustable using the value of L, because this gives us the time for which we still have a current flowing through the R. Okay? So we consider, now we look at the line with a termination that is an inductive resistor, an inductive load. So the line, of course, is initially uncharged, and we are connecting it to a voltage, a DC source of source resistance Z0 at a time t equal to 0. And now what we can see is that, I think this ones I'll try to change this one to the actual values of the VD, not the 2V1 plus. I think this one is a mistake on my part. Okay, and therefore this is our circuit. And what we want to look at is to see the equivalent circuit in circuit theory. It would look like this. We just have a Z0 and we have an inductor connecting it. So what is the effect of the length of the transmission line, L, that we have in here? So when the switch is closed at t equal to 0, we can expect that a voltage wave of amplitude V1 plus equal to V0 by 2 will be sent down the line, because this wave will not know what the termination is at the end of the line, neither the length of that line, and therefore the wave will travel down the line just as if the line was infinitely long, and it will arrive here at a time t given by L by V. So a reflected wave of V1 minus as a function of time will then be generated due to the mismatch at the Z equal to L, and therefore we can write that the voltage Vt anywhere along the line at the sending end or at the receiving end is going to be given by V1 plus V1 minus of t, and for all time greater than the one-way time of flight, which is L by V, where V is the phase velocity. And the current through the inductor will be given by the transmission line equation, that is IL of t equal to 1 over Z0 V1 plus minus V1 minus of t divided by the characteristic impedance of the line. So that's the current through the inductor, and that's the voltage through the inductor. And these equations are called transmission line equations because we are using the line voltages. Now, circuit theory tells us that the voltage across an inductor is proportional to the time rate of change of the current through it. And therefore, you can immediately write that VL of t equal to IL DIL on dt. I think this we should put an L as well. And hence, we can always write that we can express the reflected component in terms of the inductor voltage and the amplitude of the wave. And the I of L of t can also be written as that. And we get that VL of t is going to be given by 2V1 plus minus Z0 IL of t. So at the load end, the equivalent circuit of t greater than t is of the form shown, and we can therefore write that the L d IL dt plus Z0 IL of t is equal to 2V1 of t for all time greater than t. Or in other words, we can write that IL of t is equal to 2V1 plus over Z0 into 1 minus exponent of that equation there for all that time. And I of t is going to be equal to 0, and IL at infinity is just going to be equal to 2V1 plus 1. So what we have done here is to solve this problem. There are two ways in which you can solve this problem. One way is to use the Laplace transforms that you have already studied in circuit theory, or two, you could use that method which we call the Lagrange method of variation of variables, okay, or what you would call an integration factor, so to speak. So I'll give you a few minutes to try and solve that problem, okay, as given there. Could you quickly write that the Laplace transform of that, assuming that we have 0 initial conditions? The rest conditions are 0. So express that into a Laplace transform equation. So anyone with a solution for it? Are you guys working?
Yes. So you are asking for the final solution or the...
Yeah, the Laplace transform. Did you get it?
Oh, yes, the Laplace transform.
Uh-huh.
S times L I of S plus Z naught times I of S is equals to 2V1 plus over S.
That's correct. Then you can use either the partial fraction expressions and use the residue theorem to get the A's and the B's. Then you'll get this final solution as it's shown. What we are saying is that since this equation is only valid after the wave has arrived at the load termination, and that's why we have to use the time t greater than the one-way time of flight of that particular wave, starting from the sending end to the receiving end. That's why we get this equation valid, and that's why we are writing it as t minus big t for t greater than t. Or we could just even leave out the t here if we already have this value here. So the voltage across the load is therefore going to be given by the circuit theory solution, that is Vn of t is equal to L di L dt, and therefore we can differentiate that with respect to time and multiply it by the inductance, and we'll get a value for the voltage. And therefore we can get the reflected voltage as shown, and we'll get, just by subtracting this from the value of VL and V1, and we'll get a value of that nature with minus a half there. So what I usually find out, people usually make the following mistakes. Once they have seen that the line is terminated in an inductor or a capacitor, they simply assume now they can use the reflection coefficients using the j omega L, the impedance of the load. And like I said, as long as we have transient conditions on a line, we cannot use those steady state equations that you have solved or you are used to using in circuit theory. You have to remember that now these functions are changing, because initially we know from physics that the voltage across an inductor or the current through an inductor cannot rise instantaneously, because the inductor will initially oppose the increase or the change in current by introducing a very high back EMF such that that current will be zero, and in the steady state the inductor will become a short circuit. And that's why we cannot talk about a reflection coefficient, because as time varies, the load that the signal is seeing will be changing with time. And we cannot talk about impedances because we are yet to formulate impedance in the time domain. Impedance is a frequency domain concept, so to speak. So at any z equal to z1 along the line, the voltage will be V1 plus, as long as the reflection component has not arrived from the termination. Okay, so at t minus t less than L minus Z1 over V, where Z1 is between the load and the sending end. It then equals V1 plus V1 minus at T minus big T thereafter. And the voltage function can therefore be illustrated as shown. That is, once we throw the switch, the inductor load will start to, or the inductor voltage will start to increase from, or the current will start to increase from zero exponentially and approaching a final value of 2V1 plus over Z0. The inductor voltage will first of all start from twice V1 plus, and it will reduce down as time goes by. and it will be 0 thereafter, after a long time. That is the characteristic time constant. If we look at the reflection coefficient, it will first of all jump up, and then it will start to decrease and become negative as time goes. Okay, and therefore the line voltage at the point will start first of all at the level of V1 as the voltage is moving towards that position Z1, and then it will jump up and then start decreasing towards the end of the line. This should be T, not Z. So we note that T1 minus T is just going to be by L minus Z1 by V, and this gives us a value of twice T minus Z1 by T. That is at the time for which we are dealing with for this particular case. So for a capacitive termination, as shown below, again, we'll write the equations as before, and therefore, before we continue, I can ask you to write down the transmission line equations for that particular situation. Remember, we are trying to write them at the termination Z equal to 0 at this point. So you write down the transmission line equations, and we can see what you have. Do you have already the questions? Well, then I'll continue, and we'll see that the circuit theory equation is that the current through a capacitor is going to be proportional to the time rate of change of the voltage across the capacitor. And for the time t greater than t, we therefore need to solve the solution, or solve the problem at C dVc dt plus 1 over Z naught Vc of t is equal to twice V1 t plus over Z naught, where V1 plus is equal to V naught by 2, so to speak. what we have done is that we have, of course, written the transmission line equations. That is V1 plus V1 minus of t is equal to Vc of t, and IC of t multiplied by Z naught is equal to V1 plus minus the V1 of t. And therefore, we can express the V1 of t in terms of IC of t and V1 plus, and then put it in the equations, and then we can get a value for the Vc of t in terms of the current IC of t in terms of Vc of t and the V1 of t, and then we'll get that value there. Again, we use Laplace transforms as before, and we'll get a value for the voltages. And thus, Vc of t is just going to be given by that equation there, where we have a time constant that is Z naught multiplied by C, and the current will be given by that value. And then you can get the voltages and the reflected components of the voltage as shown there, okay? And we can then draw them as shown. Now, this, of course, follows what physics says, that the voltage across a capacitor cannot instantaneously rise from zero, and therefore we see that this also conforms to your circuit theory. And you can see that the current will first of all shoot up, because the capacitor will appear as a short circuit initially. If the capacitor is uncharged, it will be a short circuit, and then as it starts getting charged, it's now start going to an open circuit, and the current should then go to zero. So the reflected voltage at the load end, that is at the capacitor, will first of all shoot to the negative direction, and then again charge towards V1 plus, which is the voltage across the capacitor. At a point Z1, then the current or the distribution of the voltage will first of all be at a value of 0, then it will go down to a negative value, then start charging towards the twice V1 plus there, which is V naught. So we note again that the T1 minus T is just going to be given by that value that we had. That is the twice the round trip time of flight less the time required for the voltage to start from 0 and reach the Z1 position on that line. So the reflection, now we are through with the transients, and now we want to see how you can use the steady state computations. We have seen that we can always get the computations by writing down the equations, that is the transmission line equations, and then trying to solve for the different points. Well, in the early days, before the introduction of the computer or this computer-aided computations, it was a very difficult affair, because we can see that most of these quantities that we'll be dealing with will be complex, and sometimes you are dividing them, sometimes you are multiplying them, and therefore you would have to be very ardent with your computer, with your calculator, to change them from polar representation to rectangular representation as you are adding them up, or as you are dividing them. And therefore, Mr. Smith formulated a nice graphical way of trying to solve these problems. Today, the Smith chart is not used as much, because the computer can do the crunching, the number crunching for you with no problem. And today we even have computer calculators or handheld calculators that can can deal with complex addition or arithmetic straight away without having to change them from one form to the other. So the reflection coefficient at the load ZL, that is terminating a lossless transmission line with a characteristic impedance Z0, will be given by gamma L equal to ZL minus Z0 divided by ZL plus Z0. And we saw that this could be written as the modulus of the reflection coefficient multiplied by the phase angle of that reflection coefficient, because whenever ZL is a complex impedance, or the Z0 is a complex impedance as well, especially when we have losses, but this time we are dealing with a lossless transmission line, therefore Z naught is real, then the gamma or the reflection coefficient will be in general a complex number. So Z naught will be given as the square root of the inductance per unit length divided by the capacitance per unit length. So we can normalize the load to the characteristic impedance on the line and define a dimensionless quantity ZL. This ZL is now not a distance, but it's a normalized impedance, which will always be greater than or equal to 0. Well, this is not really the case. It could be, it can be larger than unity. So I think this one is not a very nice thing to write here. And we can write it as ZL equal to ZL over Z naught equal to RL plus JXL. So this remind me to change this addition or this comment here. So thus, if we were to take the real part of gamma to be gamma R and the imaginary part to be gamma I, then we can write the reflection coefficient in terms of the Cartesian form, that as gamma R plus J gamma I equal to RL minus 1 plus JXL over 1 plus RL plus JXL, where what we have just done is that we have divided through by Z naught everywhere in the equation ZL minus Z naught over ZL plus Z naught. That's why we have the gamma RL minus 1 over 1 plus RL or plus JXL. So this will be normalized to Z naught, and that is normalized to Z naught as well. So RL is just the big RL divided by Z naught. XL is the big XL divided by Z naught, where those are the reactances. Or equivalently, we could express now the normalized load in terms of the reflection coefficient on the line. And this, when we do that, we can just get a value of that nature. So try and ascertain for yourself that this is the correct equation that you need to deal with. Could you quickly convert, write the RL and XL or the ZL in terms of the reflection coefficient? Yeah, you guys, you need to work with me. Have you obtained this expression yet?
Not yet, almost.
Yeah, the best way to deal with it is just to use this equation here. Let me show you. Just use this equation that gamma L is equal to ZL of minus Z naught over ZL plus Z naught. Then obtain ZL in terms of Z naught and gamma L. Then do the normalization and then the splitting it into real and imaginary parts. That will be much easier than having to work from this directly. So I'll just assume that you are able to do it and then continue then. So we can therefore see that we can separate this one into real and imaginary parts by multiplying the bottom by the bottom and top by the conjugate of the denominator. And what we'll see is that RL can be written as in that form, and the XL can be written in that form there. Okay, and this is where we'll start to get the manipulation of these values to try and get the Smith chart coming out. So for a given value of RL, then the locus of the reflection coefficient will describe a circle that is specified through the equation gamma R minus RL over 1 plus RL all squared plus gamma I squared is equal to 1 over 1 plus RL. This is obtained from this equation here. Okay? That is, we can express this one in terms of a circle, an equation of a circle, okay, of this form, of that form. And I think that one is also something you'll have to ascertain for yourself after this class, that you can express these equations in terms of a circle, and the equation of a circle is usually given as x squared plus y squared equal to r squared, where r is the radius and the x and y are the coordinates in the x and the y. Okay, so that will give you whatever the equation of a circle. So try to make sure that one of them will be, you can say y is the gamma I and x is the gamma r, and then you see that it will be offset. It's a circle that is offset in that form. It will be offset by a value RL over 1 plus RL, and this one will be at the origin, that is at 0, and the center, that is the center of the circle, will be displaced by the value of the resistance that we are dealing with. And the radius of that circle is going to be 1 over 1 plus the RL, the normalized real part of the load. So the center of the R circle, this will be called an R circle, and will be located on the complex gamma plane. That is where we are plotting imaginary gamma by the real gamma, and it will be centered at a point RL by 1 plus RL and 0. And that is, it will always be along the real line. That is, the center of the circle will be along the real axis, okay, displaced by the value RL over 1 plus RL, and its radius will be 1 over 1 plus RL for each RL that you use. That is, as R changes from 0 to infinity, the radius will be of the circle will be decreasing from an infinite radius, which is a straight line, to an infinitesimally small radius, which is a point. Okay, so it will be decreasing towards a point. So XL as well will form another family of circles with an equation given by the real part of gamma minus 1 all squared plus the imaginary part of gamma, part of the gamma minus 1 over XL. And we can see that this will be centered at 1, okay, along the real axis. It will be along 1, and then it will be varying along the imaginary axis at 1 over XL. And its radius will be 1 over XL. And therefore, as XL goes to 0, that is, we have a load that is purely resistive, then we see that the center of the circle will be at infinity, okay, and its radius would be infinite as well, and therefore it will be a straight line as well. So the X circles will have a radius of 1 by XL and are centered at the point 1, 1 XL, 1 by XL. And the Smith chart is thus a graph of R and X circles in the complex gamma plane for gamma, that is the magnitude of gamma less than or equal to unity. So an example of the impedance Smith chart is illustrated below. This you must have met in your circuit theory in third year, and therefore there is nothing much to talk about. So the circles that are centered along the imaginary or the real part or the real axis of the gamma plane, okay, complex gamma plane, will be round circles that are decreasing, and for R infinity, we'll get it at that point. And R infinity is what we call the open circuit condition of the line, and therefore if R is equal to 0, it will be at this point, and therefore this will be the short circuit point, and that is the open circuit point. Remember, the origin of the gamma plane is at that point, okay? And therefore, when you are at this point, it means that R is equal to the Z0 of that, or equal to the characteristic impedance of the line at this point. And it will always indicate a matched condition for that particular transmission line. So the circumference, the largest R circle or the gamma circle is unity, and therefore this gives us where we have either an open circuit or a short circuit where gamma, the magnitude of gamma is unity. So it never goes beyond that. So the fractional distance from the center of the chart to a given point relative to the radius, gamma, that is the magnitude of gamma equal to 1 of the circle, is a measure of the value of gamma at that point. What do we mean by this? We mean that if you were to draw this a line starting from there towards the perimeter of the gamma circle, no, or the unit circle in the gamma plane, then any point along that line compared to the length of that line, that is unity, will be the value of the magnitude of gamma for that particular point. That is, if you were to put a line straight, just draw a line straight away across from the center of the chart, that is the origin of the gamma plane, to the unit circle, any distance that you measure relative to that will just be equal to the magnitude of that gamma. So the theta gamma, that is the angle of the reflection coefficient, will be the angle that this line from the center passing through that given point makes with the real axis. That is, if we draw that line in this direction, then we measure the angle in that form. If we drew it like that, the angle would be that form. Okay? Or the negative part of it.
Excuse.
Yes.
Is there any particular reason for the imaginary arcs that are tangential to the line, to the horizontal line for the real part?
Which ones? This one.
The arcs. Yes, those arcs. Is there any particular reason they're tangential?
Okay, we looked. Yeah, there is a reason for it because of the following case. You can see how this is the center of the circle, of the X circle, is given by that value.
Yes.
Okay? So what it means is that XL can be negative or positive. True?
Yes.
Because it could be inductive or negative or capacitive.
Yes.
Agreed?
Yes.
So when you have that, so it's my value. Here it is. So for positive X values, the centers will be varying towards positive infinity. Agreed?
Yes.
Along this point, along this line here, X R equal to 1.
Yes.
Okay? So if it's negative, it will be going down this way. And since we don't want the circles outside the unit circle, we don't need them. So you can see that there will be two circles forming a figure 8, isn't it? About the real axis.
Yeah.
Not true?
Sorry, I'm not seeing the figure 8 coming about.
Okay, what I can tell you is this. Did you see this circle here?
Yes.
Imagine it is complete.
Yeah.
And this circle here is a similar one, isn't it?
Yes.
It's for the negative part of that x. Now imagine it to be complete. Is that not a figure 8?
Oh, yes, yes.
Yeah. So the reason why it's like that is because this is a circle that will have the largest, that has a very high whatever. You know, when the center is at, if we say like xl is equal to 0, okay?
Yes.
The radius will be infinite.
Yeah.
Isn't it?
Yes.
So if the line is at infinity, the circle will be, that you can draw will be this line. Correct?
Oh, yeah.
If you are at negative infinity, it's again the same line you'll be drawing, isn't it?
Yes.
So you can never cross those two lines. So that's why they are all tangential to it, because the centers are varying along a vertical line.
Okay, thank you.
Yeah. So, well, how do we say? So the gamma theta, that is the theta gamma for the reflection coefficient, will therefore be the line that you draw from the center of the chart to passing through the point that you are dealing with. Okay, the angle it makes with the real axis and the positive real axis, so to speak. And thus, a gamma circle, remember, a gamma circle will be drawn, has a center of 0, 0. That is at the matched point, the center of the chart. So the gamma circles, as reflection coefficient circles, will be drawn with this center, and therefore they are concentric, all of them, with the largest one being the unit circle. Okay? So if we draw them around here, we'll just be getting the values of the gamma circles. So a gamma circle will intersect the real axis always at 2 points. One, at a point PM towards the open circuit point, that is the point R equal to 1 and X equal to 0, that is to the right of the origin, and a point PM towards the short circuit point at R equal to 0 and X equal to 0, that is to the left of the origin of the gamma circles. So it will always cross the real axis at 2 points, always. So the PM and the P small m will represent a case of a pure resistive loading, since now the XLs are all equal to 0 for this particular resistive loading, and therefore it's a loading, a resistive loading on that line, with PM representing the case where the load resistance is larger than the characteristic impedance of the line. And PM will represent the resistive loading with RL less than Z0. I hope, do we get me? Or I have to go back again?
Yes, please do the point.
So we are saying that P big M will be on this side, and P small m will be on that side. Now imagine we draw a circle about the origin there. So what we are saying is that that circle that we draw here will cut the the real axis at that point and that point. Okay? So this point where it cuts the real axis towards the big PM will be for a case where the normalized load resistance, or the load resistance, is larger than the characteristic impedance. Remember, all points along the real axis here are for the case of the ZL, or the load impedance, being purely resistive, so that all the X circles have centers at infinity, and therefore they just lie on this line. Okay? So if it's on this other side, we'll see that RL will be smaller than Z0. That's why we have it on that end, on this other end, and we are going towards the short circuit. That's what bullet is trying to explain. Have we got it now?
Yes, yes.
Now, when RL is greater than Z0, remember we have already seen this before. When at Z0, we know that the reflection, the voltage standing wave ratio S will be given as RL divided by Z0, and therefore it will be the same as the normalized resistance or load resistance. And therefore, any number that you get along the line, that is any point where the gamma circle is crossing that real axis, will give us the reflection coefficient, not reflection coefficient, but the voltage standing wave ratio for the case where RL is larger than Z0. So we can directly read from the Smith chart the reflection, the voltage standing wave ratio for that particular case. And hence, we can say that the R circle that is passing through PM will be numerically equal to the standing wave ratio, okay, on that line. The value of the R circle passing through small pm will then be equal to 1 over R over S. So for a lossless line, the impedance looking toward the load at a plane minus Z from the load is given by Zi at minus Z. Remember, we are measuring Z now at the load, and by saying minus Z, we are going towards the generator. And therefore, it will be V of minus Z by I of minus Z, which we already obtained as Z0, 1 plus gamma exponent of minus J 2 beta Z over 1 minus gamma exponent of minus J 2 beta Z. We can therefore change this one into the modulus and add in the angle of the reflection coefficient. This is where we have already seen this. That is, the load is at the Z-axis, is at the origin of the Z-axis. So when we use normalized impedances, we can therefore, the only thing we need to do is to divide through by Z0, and we get that the normalized input impedance at that point is going to be given by that value, which we have written here as 1 plus 1, the modulus of gamma plus times the exponent of J phi over 1 minus the magnitude of gamma and multiplied by the exponent of J phi, where J phi is defined as the phase angle of the reflection coefficient minus twice the electrical length at that particular point. So if we travel along, or we go around the Smith chart along a constant gamma circle, and we subtract, that is, we rotate clockwise from gamma theta, theta gamma through 2 beta Z, which is equal to 4 pi Z by lambda, we locate the point, that gamma that we have there, exponent of J phi, the reflection coefficient of the input impedance at distance Z from the load. So example, use the Smith chart to determine the input impedance of a section of 50 ohm lossless line that is 0.1 gamma lambda along the terminated and terminated in a short circuit. So what we do is that we recall that ZL has been given as a short circuit, therefore the normalized ZL is going to be equal to 0. The Z0 we have been told is 50 ohm, and the minus Z is just about 0.1 gamma. On the Smith chart, we'll mark the short circuit point, which is to the left of the origin, and at the intersection of R equal to 0 and X equal to 0, that is that point, then we'll move along the circumference of the chart, because the gamma that we have now is going to be unity magnitude, and we'll move a distance 0.1 lambda towards the generator, okay? That is clockwise, in a clockwise direction, and we'll arrive at a point P1 as shown there. At this point, we'll read off the value of R. R is going to be equal to 0 because R is only along this line. So R is 0 there, and the X is going to be approximately 0.725, or Zi is going to be given by J 0.725, which is equal to Zi. Big Zi, now denormalize it, and we get a value of J 36.3 ohm. So we want you to confirm this using the actual equations here. The actual equation, the equation like this. Okay. So use this equation to try and see whether you can get that value of this value here, that 6.3 ohms. So a lossless transmission line of length 0.434 gamma lambda and characteristic impedance of 100 ohm is terminated in an impedance of 260 plus J 180 ohm, and you are required to determine the voltage reflection coefficient, and B, the standing wave ratio, and C, the input impedance and the location of the voltage maximum on that line. So what we are given, the information is as follows. I'm using the minus because I've located my origin at the load. So I'm using the minus for the direction towards the generator. So the length is 0.431 lambda. The Z naught is 100 ohm. ZL is 260 plus J 180. And therefore we can get the normalization of the normalized load as ZL by Z naught, and we get a 2.60 plus J 1.8. And the gamma, okay, the magnitude of the gamma is just going to be 0.60. So we'll plot on the Smith chart the point P2, which is just 2.6 and 1.8, and draw a circle of radius 0, that is from the origin to that point, okay, equal to gamma. And that is, we'll measure as a radius of 0.6, and we'll, at the point T, we'll just draw a radius of that value. We then draw the line OP and extend it to the point P1 prime on the unit circle, and then read off the length of the line toward the generator, and this would appear as 0.220. This you can go try, and I've already solved this problem, so it's for you to go and try and see whether you get these values here. You are experts at using the Smith chart already, I've been told. So the first angle of the reflection coefficient will then be given by 4 pi multiplied by the 0.250 minus 0.22, where this is the circle itself, and we can get that it's about 0.12 pi or 0.38 radians, which is about 22 degrees. Multiplication by 4 pi is, of course, because the angles on the Smith chart will be given in terms of twice beta L, that is the electrical distance or length beta L twice, which is 4 pi by lambda, and multiplied by L. And thus, the gamma will be given as that. And B, the 0.6 gamma circle will intersect the positive real axis at a point OP or C at R equal to the standing wave ratio of 4, so that the voltage standing wave ratio is just simply 4. And for the C, the impedance advanced, for the impedance you advance the P prime, which is at the perimeter of the Smith chart, through an angle or a length 0.434 lambda towards the generator to a point P3. Okay, first to 0.5, because once you go around, you'll go around you'll go around the Smith chart, and therefore you'll be at the same position. And further 1.54 to get to a value of 0.28, and then you'll get a value of that. So since a complete evolution around the Smith chart corresponds to a length of lambda by 2. So I don't know whether this, I have to go through that. You can go through this yourselves in the class notes themselves and the slides. And this is what we've been talking about. This is where we're talking about. So this is what we are calling the 0.6 gamma circle. Okay, we have that P3 and P prime. We have that P2 and P prime, and that's the POC we are talking about, or the open circuit point, and that is the short circuit point, and that is the PM we are talking about. This is where that gamma circle crosses, and this, the value of the R circle that is passing through there would give us the standing wave ratio. So that's the Smith chart solution. So I'll now skip this and see that I think I'll give you a 5-minute break, and then we can continue from there. I don't think I want to go on just talking about the examples, because the examples will just be a little bit repetitive. So how much do I have left? So the other thing we need to talk about may be the impedance matching, and that one is already something I've dealt with, and that one I won't talk about. So I'll leave you to go through this one by yourselves. Try to see whether you have any issues, then we can raise them in class, and then we can continue with another thing. Take a 5-minute break then. So we'll now look at the general properties of the uniform section waveguides. I hope you can see this particular shared, or if it's not, you can always change. Let me stop representing and then. So I want to share another one. So you can see that document there.
Yes.
So we are going to look at wave propagation along uniform guiding structures. Now we are now going into the realm of where we have only a single conductor, or structures that have only single conductors to guide the wave. So without loss of generality, we can always assume that the waves are propagating in the positive z direction, and the propagation factor has the form of exponent of j omega t minus gamma z, where gamma is equal to alpha plus j beta. The guide will be oriented with its axis along the z-axis, and then it will be filled with a dielectric with constitutive parameters mu and epsilon, which may be complex to represent losses in that dielectric. Now we consider a metal pipe, say for example a water pipe, but now we are saying it has an arbitrary cross-section but uniform, okay, and it's filled with a dielectric and with its axis oriented along the z-axis as shown. So the z-axis in that direction, the y is the vertical, and the x is moving in that direction in a right-handed Cartesian coordinate system. So at a charge-free point in the dielectric, the electric and magnetic field intensities will be solutions of the homogeneous Helmholtz equations that the Laplacian of E plus k squared E equal to 0, and the Laplacian of H plus k squared E H is equal to 0, where k is just simply omega root mu epsilon. K could be complex, but for now we are just going to assume that this is the usual form of the K, which is the wave number. Now, when we use the TE and TM decomposition of the fields, that is transverse and axial field components, the transverse field components will then be related to the axial components, as we saw already at the beginning of the course. That E of t is going to be given by j omega mu gradient of h of z with the direction vector minus the gamma by kc and the gradient of the z component of the electric field intensity. And the ht can be expressed likewise in terms of the axial field intensity components, and where the kc squared was given as gamma squared plus omega squared mu epsilon, or gamma squared plus k squared. Now, depending on the values of hz and ez, we can have transverse electromagnetic waves when ez and hz are equal to 0, transverse magnetic or tm or e waves if ez is not equal to 0 and hz is equal to 0, and transverse electric or TE or H waves where we have Ez equal to 0 and Hz not equal to 0. All the hybrid modes where the solution must require both TM and TE by superposition to be present in that line. So for TEM waves with Hz equal to 0 and Ez equal to 0 within the guide, okay, and will exist only if we can have the propagation constant gamma of TEM waves plus k squared equal to 0. In other words, the gamma TEM must be equal to an imaginary k, that is j omega root mu epsilon, where mu and epsilon are assumed to be real scalars. So this value, these waves will propagate with a phase velocity Vp given by omega divided by k, and it will give us a value of 1 over root mu epsilon, which is the same as the intrinsic the phase velocity for that wave in the medium when unbounded. The intrinsic impedance, or the wave impedance for TEM waves, we have already seen this will be given by ZTEM equal to EX divided by HY, or the minus of EY divided by HX, and this will give us something like J omega mu by gamma TEM, and we see, and it's also going to be given by gamma TEM by J omega E, and epsilon, which is equal to root mu by epsilon, which is equal to eta, just like in the unbounded medium. And we note that for a Y-polarized wave, that the wave impedance is going to be given by EY by EX, which is equal to the minus of eta. So hence, we can get the value of the H component, or the magnetic field intensity, can be written in terms of the electric field intensity as Z cross E and divided by the intrinsic impedance eta that we have already obtained. Since magnetic field lines will always close on themselves, that is, whenever we have a magnet, we can always cut it into as small a magnet as possible, but the lines will always have a north pole and a south pole. So the lines always close on themselves because they are created by a current, and the current does not flow through breaks. The current must flow through a closed circuit, so to speak. So these lines form closed loops in a transverse plane for TEM waves to exist in a waveguide. They must have closed loops. Now, from the general Ampere's law or circuit law, the line integral of the magnetic field intensity in any closed path in a transverse plane is then equal to the sum, or to the total current enclosed within or threading that particular path that we are dealing with. That is the sum of the longitudinal conduction and displacement currents enclosed by that path of integration. In the absence of an inner conductor, therefore, there will be no axial current that can exist inside the waveguide, and hence no closed magnetic loops in any transverse plane can exist. And therefore, we must conclude that for hollow waveguides or waveguides with single conductors of any shape, there is no support for TEM mode of propagation. So TEM modes cannot propagate on a waveguide. So let's look at E modes, or the TM modes, where EZ is not equal to 0, but HZ is equal to 0. Therefore, it's entirely transverse to the direction of propagation. And therefore, E of t, that is the transverse component of the electric field intensity, is going to be given by the minus of gamma by kc squared, multiplied by the gradient of Ez. Remember, Hz being equal to 0, the Z cross gradient of Hz is going to be equal to 0, and that term is omitted, it falls out. So taking the transverse divergence of E, we can obtain the following. That is, we'll multiply that one, we'll take the dot product of that with the del operator, and we get a value of gamma E of Z, which is equal to the minus of that, this using the what we call the auxiliary form of the Maxwell's equations, that is the Gauss law, and we'll get a value of minus gamma by kc squared del squared Ez. Or in other words, the Laplacian of Ez plus kc squared Ez is equal to 0. So this is a wave equation, or a Helmholtz equation in terms of Ez and the transverse, in the transverse plane. So with Hz equal to 0, we can then write that H of t is going to be given by the minus of j omega epsilon by kc squared Z cross the gradient of E of Z. And since the gradient of E of Z has been given here as the minus of kc squared by gamma and multiplied by E of t, then we can see that H of t is going to be given by j omega epsilon by gamma multiplied by Z cross the E of t. which we can see, we can define this as 1 over impedance, and we are going to call it 1 over ZTM, Z cross E of t, where ZTM, that is the wave impedance, ZTM for TM modes, is going to be given by gamma by J omega epsilon, and we call it a wave impedance for the transverse magnetic wave. With Kc squared equal to gamma squared plus omega squared mu epsilon, then we can see that gamma can be obtained in terms of Kc and the K as the square root of Kc squared minus omega squared mu epsilon. And we define Kc squared to be a value omega c, where omega c is some characteristic in radiant frequency multiplying mu epsilon. That is, we can write Kc as twice pi divided by a wavelength lambda c, and we'll call it the cutoff wave number for the given mode in that guide. Now, we can then define a corresponding frequency, Fc, as Fc equal to Kc divided by twice pi root mu epsilon, and we see that this is just Kc by twice pi multiplied by c, where c is just simply 1 over root mu epsilon. That is the speed of light in that medium between in the waveguide. So, if the guide is operated at a frequency f equal to Fc, then we see from this equation here, okay, since this one has an Fc and that has an F, if this one also is omega c as this one is omega c here, what would happen is we'll have a 0 and gamma is going to be equal to 0. So if gamma is equal to 0, then it means that wave is not propagating in the z direction at all, because remember, gamma was multiplying z in the expression for the fields. And if gamma is equal to 0, then the wave is standstill. It's not moving in space. So Fc is therefore called the cutoff frequency of the given mode in the waveguide. And the value of Fc for a given waveguide mode will depend on Kc for that particular mode. So thus, gamma can be written as J omega by C root 1 minus f of c divided by f all squared. So this is the factor, the frequency factor we saw before when we were dealing with the classification of the propagation modes of waves. So if f of c by f is less than unity, gamma is going to be imaginary and is going to be given by j beta, which is equal to jk root 1 minus kc by k all squared, or we can replace that one with the values for omega, that is omega c by omega here, okay, and we get f of c by f all squared. The wave will hence propagate down the guide with a phase propagation constant beta equal to omega by omega c equal to 1 minus f of c by f. Remember, for this condition, we mean that we will operate our waveguide at a frequency above the cutoff frequency f of c. The wavelength associated with beta is called the guide wavelength. That is the wavelength for the signal that is propagating along the guide. And the lambda g is therefore going to be defined as twice pi by beta, and we see that it's going to be just lambda over 1 minus f of c and 1 over f all squared. And this we see is going to be larger than the actual wavelength of the signal when propagating in the unbounded medium. So if we define lambda c as c divided by f of c, then we can see that they will be related, that the wavelength in the unbounded medium, okay, 1 over lambda squared is equal to 1 over the guide wavelength squared plus 1 over the cutoff wavelength lambda c squared. The phase velocity of the mode propagating in the guide is given by Vp equal to omega by beta, and we see it's the c divided by 1 minus f of c over f all squared. And since f of c over f is positive, the squared is positive, then 1 minus will always be going to be larger than unity, and therefore we see that the phase velocity within the guide is going to be above the value of C in the ratio the guide length over wavelength divided by the unbounded wavelength of the signal multiplied by the C. And we see that this is going to be larger than the C, that is the speed, the phase velocity of the wave in the unbounded medium. Note, lambda g we have seen is larger than lambda, and therefore this is true, is a true relation there. So we say that the phase velocity in the guide frequency is frequency dependent and always greater than the phase velocity of the wave propagating in that bounded medium. And because it's dependent on the frequency of the signal, then the waveguide is just going to be inherently dispersive. That is, high frequency components will be traveling near the speed of light in the unbounded medium, while the low frequency ones will be traveling slower. So hence, waveguides will be dispersive, and the group velocity can be defined for the mode in the guide and given as Vg equal to 1 over the derivative of the propagation constant, or the phase propagation constant with respect to the radiant frequency, and we get that is going to be given by C multiplied by the frequency correction factor, and we see that is going to be smaller than C. So we note that if we multiply Vg and multiply it with the phase velocity, we'll get a value of C squared, just like we have seen before. So in a lossless guide, signal propagation or velocity of energy transport will then be equal to the group velocity. The wave impedance for the propagating modes is then purely resistive and will be given by ZTM equal to eta root 1 minus f of C over f whole squared. Remember, propagating modes are modes for which the operating frequency f is larger than the cutoff frequency. The variation of the wave impedance for TM modes, when normalized to the intrinsic impedance of the medium, okay, and the frequency normalized to f of C, we see that it will be having the following form. That it will start from 0, okay, at f equal to f of C, and this impedance will be increasing and moving towards a final value of unity, that is Z naught, or the eta that we have for the unbounded medium. That is, as the frequency, the operating frequency is increased from f of C to infinity, then we'll have that wave impedance approaching the intrinsic impedance of the medium. Note, for frequencies below f of C, the wave does not propagate, and we call this region the evanescent region. There's no propagation, and the ZTM does not have any definition here. It will be imaginary. So if f of C divided by f is greater than unity, then gamma is going to be real and will be given by a value of J, f equal to gamma equal to alpha equal to omega C by C root of 1 minus f over f of C. And the wave decays rapidly with increasing Z, that is away from the sending end, and is then said to be evanescent. The wave impedance for the evanescent modes is purely reactive and given by ZTM equal to J eta f of C by f into the root of 1 minus f by f of C whole square, which is then hence purely reactive because of that J. So for the H modes, the Ez is now equal to 0, Hz is not equal to 0, and we can therefore write the transverse magnetic field intensity in terms of the gradient of the Z component of the Hz, or the axial component of the magnetic field intensity in that form. And we take the divergence of H of t, and we remember that will give us a value of gamma multiplied by h of z, and we get a value of minus gamma by kc squared and multiplied by the Laplacian of h of z. Or in other words, the magnetic field intensity, the actual field intensity will satisfy that transverse Helmholtz equation homogeneous. And we have the gradient of h of z is given by that equation there, and therefore we can get a value of E of t as j omega mu by kc squared z cross h, the gradient of h of z, and we get a value of the minus of zte z cross h of t, where zte or the wave impedance for te modes is going to be given by j omega mu divided by gamma. The propagation constant for TE waves is also going to be given by that equation there, gamma equal to kc squared minus k squared, and we see that it's exactly the same as for the propagation constant for the TM modes, as long as they are propagated, so to speak. So if f of c by f is less than unity, then gamma will be imaginary, and the wave will propagate in the guide with a phase propagation constant given by j beta, j omega, which is j omega by c and root multiplied by the frequency correction factor. And we note that it's exactly the same as for the TM modes. The wave impedance is then purely resistive and will be given by eta divided by 1 over 1 minus f of c by f all squared. And it will be larger than the intrinsic impedance for the unbounded medium. Note, as f, the operating frequency f, approaches the cutoff frequency f of c, then the ZTE approaches infinity. That is, we'll start from a very high impedance, okay, for the evanescent modes, and then we'll decrease the impedance as the frequency increases towards infinity to come to the value of the intrinsic impedance of that medium. So f of c less than, over f greater than unity means that the gamma is also real, and we'll get a value of that nature, just like before. And the wave impedance is just going to be given by it's going to be purely imaginary reactive, and it will be given by that eta over 1 minus f by f of c there. So the variation of the transverse electric intrinsic impedance, or the wave impedance normalized to the intrinsic impedance with frequency, is shown below. And we start from a very high frequency, very high impedance, okay, at f of c, and this decreases towards unity as the frequency is increased. This region here below f of c is going to be the evanescent region. So, question or example 1. Part A, determine the wave impedance and guide wavelength at an operating frequency equal to twice the cutoff frequency in a waveguide for TM and TE modes. And B, repeat for a frequency equal to 1/2 the cutoff frequency. And C, what are the wave impedance and guide wavelength for the TEM mode? Of course, for TEM mode in a waveguide, this one will not appear. Those ones should be 0, so to speak. The TEM modes are not supported in a waveguide. But if you look at that equation there, that is half the cutoff frequency, the wave will not be propagating, and therefore the impedance is going to be imaginary. The guide wavelength will also have no meaning because there will be no propagation. But let's see what we have as a solution. So at f equal to 2fc, we can write that f of c by f is just going to be equal to 1/4, that is 1/2 squared. And therefore we can get the frequency propagation correction factor is just going to be given by √3/2, which is about 0.866. And therefore ZTM is going to be given by 0.866 eta, and is less than eta, and lambda TM is going to be given by that value there, where we are dividing by that 0.866 to multiply lambda. And ZTE is going to be given by that value, and the gamma TE is going to be given by the same value there. So at F equal to 0.5 FC, no propagating modes will exist on the guide, and therefore the guide wavelength will have no meaning. Okay, it has no physical meaning. The ZTM will be, of course, imaginary, and you can see it's just 3 root multiplied by eta for ZTM, and it's going to be given by eta by root 3 for ZTE. And for the TEM modes, okay, we'll exhibit not cutoff frequency or cutoff characteristics, and usually for a waveguide, the TEM modes don't exist on that guide, okay, unless at very high frequencies such that the walls of the guide are very far compared to the wavelength of that signal. So this one is just purely just to show what TEM modes would be behaving like, but not in that guide. So modes, so for propagating modes, we can say that gamma is going to be purely imaginary and is going to be given by J beta, and the variation of beta with frequency will then determine the properties of the wave along the guide. Remember that beta is going to be related to the K through that frequency correction factor, or it's called the dispersion factor. And therefore, a plot of omega, that is operating frequency, radial frequency, against the phase propagation constant is usually referred to as the Brillouin diagram, and this is illustrated below. The straight line here that we have there is the line for TEM modes, which are not dispersive. This is where all the modes will be approaching this line, and it's usually in the literature it will be called the light line. Light as in light, light waves. So this is the light line, the straight line there. And all the others will be following such a curve, where this is the curve we have drawn for beta against omega. That is beta against omega there. So what it means is that we can always get the values of omega and of gamma and beta by just drawing this equation here. That is, to any point that there, the slope of that will give us a value for beta, and that equation value here will also give us a value for the alphas in the propagation constant there. So for propagating modes, we can write that omega is equal to beta multiplied by c over 1 minus omega c by omega, where now I'm removing, using the omega c by multiplying the f's with the 2 pi, which will not change. So we are just using the radial frequencies. And the slope of the line connecting the origin to any point on the omega beta curve will then be a measure of the phase velocity of the propagating mode with the cutoff frequency f of c in a guide operated at a frequency f. So example 2. Obtain a graph showing the relationship between the attenuation constant alpha and the operating frequency f for evanescent modes in a waveguide. So evanescent modes, we have seen that they are not propagating modes, and therefore the operating frequency f, or their frequency f, is less than the f of c of the guide. And thus, we can always write that alpha f divided by k of c all squared plus f squared must be equal to f of c, which we can see is a circle centered at the 0, 0, okay, and has radius f of c. And therefore, the value of alpha can then be obtained from the quarter circle that is bounded by the positive axis as shown below. We are going to assume alpha will always be a positive number, because in our waves, it will be multiplied by a -1 to show an attenuation. And therefore, when we draw that, okay, we get a radius of unity, because f divided by f of c, and that will be alpha by k of c. And So we can always get the value of the alpha from that circle there. So let C equal to 1 over root mu epsilon to denote the phase velocity with which constant phase points on the wavefront of a TEM mode, okay, in a boundless homogeneous medium characterized by mu and epsilon propagate. And now, in general, we can denote that velocity at which a point on a constant phase wavefront would propagate regardless of the wave type by the symbol Vp, and note that the Vp and C are identical for TEM modes. So if the velocity and attenuation in a waveguide are constant in frequency, a signal composed of more than one frequency component will then propagate down the guide without distortion, because all the frequency components will preserve their phases relative to each other. They'll always keep in pace. So whenever the phase velocity is a function of frequency, then distortion will result, with the higher frequency components especially leading the lower frequency ones at a point further down the guide. So this effect is what we call dispersion, and which can be pictured. Say, for example, if there are a group of us are climbing Mount Kenya, those ones who are energetic, of course, will go faster up the mountain than those ones who are less energetic, although we all start at the same time at the base. Or rather, you can look at guys running the 10,000 meter. You can see the real tough ones will be way ahead of the guys who are just pretending to be runners or athletes. So when dispersion exists, the wave cannot be characterized with a single phase velocity, however. And dispersion is, however, not very severe in many practical guides, especially if we drive them with narrow band signals. And a unique group velocity can then be defined for these signals. So group velocity can be defined as the velocity with which a narrow band signal propagates, and we consider a narrow band signal f of t with a Fourier transform f of j omega. And f of t and f of omega will be related through the Fourier transform pair like that. I don't know whether we have covered Fourier transforms in signal processing.
We have not yet covered it in telecommunications, but we covered it in mathematics in third year.
Yeah, okay, then we are in good state. The mathematical way, physics way, they usually use a square root of 2 pi everywhere. That is for both the forward transform and the inverse transform. But that one is to try and get symmetry. But the electrical engineering will use this more unbalanced form, where the Fourier transform itself is not divided by twice pi, but we put the twice pi in the inverse Fourier transform. So we can regard the guide in which this signal propagates as a linear system with an impulse response of h omega, which are related as in that Fourier transform pair. And at this receiving end, that is the load side of the guide, we can then express the output signal as f naught of omega equal to h omega multiplied by f omega. That is the LTI systems that you have dealt with in signal processing, or is it control engineering? I don't know. So if the guide is lossless and matched to the load, then h omega is just going to be given by a value e multiplied by the exponent of minus j beta z, which is a linear value, and we can write that one as exponent of j omega of phi omega, where phi omega is the phase response of that system. Beta is the propagation constant in the guide, and A is an amplitude constant for that. And thus, the inverse Fourier transform, or the output time signal f naught of t, will be given by that Fourier transform there, and we get a value that if phi omega is a linear function of omega, say omega equal to omega tau, then we can get that f naught of t is going to be given by that j omega t minus tau and d omega there. And we get that it's just going to be a delayed version of the input signal. That is the signal at the sending end delayed by a value tau, which is then a replica of that input signal. And thus, a guide with a transfer function of the form h omega equal to a exponent of j omega tau does not distort the input signal in any way. It only delays it or gives a time shift. In a lossless TEM propagation, beta is just going to be given by omega root mu, which is equal to omega multiplied by tau, where tau is just the inverse of the frequency of C, so to speak. And thus, there can be no signal distortion as long as mu and epsilon are independent of frequency. So when the guide is filled with a lossy dielectric, the attenuation will be a function of frequency in general, and a distortion will then occur. So if we consider a narrowband signal with a mathematical description of S of t equal to f of t, the cosine of omega t, that is the real part of f of t, exponent of j omega t, okay, this t should not be there. That is, we are using an amplitude modulated signal, then we can assume that the highest frequency in f of t is omega max, much smaller than omega naught, where omega naught is called the carrier frequency, okay? Hence, S omega is just going to be given by that Fourier transform, and we get a value of f of omega minus omega naught, the frequency shifting property of Fourier transforms. So the output signal is then going to be given by S of omega equal to a multiplied by f omega minus omega naught multiplied by that value there. And hence, the inverse Fourier transform for that output signal is going to be valid for narrowband signals with omega max much smaller than omega naught. And thus, beta omega can be written as the center frequency phase propagation constant multiplied by, plus the derivative at that center frequency and multiplied by the frequency difference or the frequency shift, and so forth. If we have more than several, what that is the complete, or the, I should be using an equal sign there because I'm showing that we have higher order terms. So if we keep only the first two linear terms, then we get that is going to be given by the center frequency phase propagation constant plus a correction factor at a higher frequency, that is for omega minus omega naught, where that is given by that value, and beta naught prime is going to be given by dB by d omega at the center frequency. So if we defined big omega here as a frequency shift, then we can see that that equation, that is the output signal, will be given by that expression there, and we see that it's going to be given by a time delay, okay, a frequency path that is propagating with the correction factor multiplied by the carrier frequency or the carrier signal that is moving at the center frequency values there. Okay, so this is a time-shifted replica of the original modulated signal envelope. Okay, that is, it's just delayed. So the velocity of the constant amplitude points, that is the f of t minus beta naught z prime multiplied by z constant, okay, is going to be given by that value there, that is Vg equal to 1 by beta naught prime, which is dB by d omega inverse at omega equal at the center frequency. So example, calculate the group velocity for a waveguide mode propagating in an air-filled waveguide and compare this velocity to the general velocity, phase velocity Vp and C. So we have beta is going to be given by k naught squared minus kc, where this is the center frequency beta, or k, and this is going to be given by omega c all squared minus kc squared. And we see that dB d omega is going to be given by k naught over c divided by beta. And the Vg is therefore going to be given by c multiplied by beta by k naught, and you can see that it's going to be less than c. So what would be the power capacity in the guiding structure? How much power do we have? The power handling capacity of an air-filled transmission line or waveguide will be limited by the voltage breakdown of the dielectric that is between the conductors. And this will occur for hollow waveguides, it will occur at the field strength of ED equal to 3 times 10 to the 6 volts per meter at room temperature and sea level pressure. So for an air-filled coaxial line with an inner conductor of radius A and an inner radius of outer conductor B, the radioelectric field intensity for the TEM mode of operation is going to be given by ER equal to V naught by R natural over B by A, with the maximum field occurring at the center at the inner conductor surface. And thus, the maximum peak-to-peak voltage before breakdown in the line will be given by Vmax equal to ED multiplied by A, the natural of B by A, and Z naught equal to eta by twice pi, natural of B by A. So the maximum power will then be given by Pmax equal to Vmax divided by twice V naught, and you see that that is going to be given by pi AED squared by eta, the natural of B by A. So at a higher Pmax will then require that we use a larger coaxial line while we keep the ratio beta B by A fixed for the same characteristic impedance. That is, for Z naught is a function of B by A, and therefore if we keep the B by A ratio constant, then the Z naught will not change. However, the A and B will determine the highest frequency at which that line can be operated mode-free. That is, before the waveguide modes start to propagate along the coaxial line will depend on the thickness of the dielectric between the conductors. And for the dominant TE waveguide mode in the coaxial line, having a circumferential field variation will be analogous to the dominant TE10 mode in a rectangular waveguide. And from physical reasoning, then the cutoff of this wave type is when the average circumference of the line is approximately equal to the wavelength, that is lambda c is approximately twice pi a plus b over 2, which is equal to pi a plus b plus c by f max, where f max is the highest operating frequency before the waveguide modes start to operate in that guide. And for a 50 ohm airline, we have that B by A is 5 by 6, or B by A is just approximately 2.3, it's meaning that A must be C by 3.3 pi multiplied by F max. And thus P max is going to be given by that equation, and you see that it's related to the field strength of the dielectric divided by the maximum frequency that you can deal with. So for a rectangular waveguide with a cross-section of A by B, A will be greater than, with A greater than B, the electric field intensity of the fundamental mode will be varying as EY equal to E naught sine pi by X by A. We shall see this when we start dealing with the rectangular section waveguides, but for now I'm just looking at the power capacity. Maybe I should have put this power capacity after we have discussed those values or those properties of the different waveguides. So thus the Pmax is going to be given by that, and we see that this is the geometries of the guide, and the Z naught is the wave impedance of that guide. And for many rectangular waveguides, okay, will be constructed with a single mode operation in mind, where A is approximately twice B to avoid propagation of the TE20 modes, which is the next higher mode, where B is called the height of the guide and A will be called the width. That's why we have a rectangular guide, so to speak. And thus we must have that A equal to C by F max, so that P max is just going to be given by that equation there. So arcing and voltage breakdown will be high frequency processes, and therefore P max represents the peak value of that particular guide. And hence, when we are constructing a guiding structure, we must provide a safety factor of 2 so that the practical P max values are approximately half the theoretical ones. So all waveguides will be designed with this criteria in mind to try and avoid arcing. So in case of reflection coefficient becoming unity, the maximum guide will then be twice the value in a reflection-free case. P max allowable must then be reduced by a factor of 4. So power handling capacity can be improved by using pressurized air. We use inert gases with a higher dielectric, whatever the breakdown strength, or we use dielectric with larger values, like higher dielectric strengths, so to speak. And that brings us to the end of that. And I propose now to stop there, and we can continue from there next week. So, any question before we break? But power handling capacity, of course, I've dealt with things that we are yet to meet, but well, I'll try to see whether I can rearrange the topics so that they appear after, but we shall get to understand it better when we look at the actual waveguides, because that's our next topic. So any question before we break then? So I'll assume silence means that there are no questions. So all I'll ask you to do is to go and try to go through that. I'll try to correct the few typographical errors I've seen. Then I'll repost it again. So be on the lookout of this. But you can continue with what already you have.
Excuse me, sir.
Yes.
For the notes in prose form, do they also have the typographical errors, or they are okay?
Which ones?
The notes in prose form.
Maximum?
The notes in prose form.
Those ones, I don't think the typographical errors are many. I've looked at them. I've looked at them several times. But if you get any, you can always point out. I can correct them.
Okay, thank you.
Yeah. But this one is because of the preparation of the slides. Sometimes I've seen even one slide that was not complete. It was actually overfilling the page. So I'll have to correct that as well. So any other question? The thing I have to point out is that electrodynamics is not different from circuit theory. So the only thing is that we are dealing with circuit theory at points. And therefore, whenever you are trying to answer problems from electrodynamics, you can always think about the circuit theory things that you have before, and you'll always find that you are always in a, you'll always be in sync. Don't try to study by putting the different subjects that you are covering in different parts of the brain. They are all related. Try to always look at the relationship. Say, for example, the circuit theory laws of Kirchhoff's voltage and current law, they all come from the Faraday's law and Ampere's circuit law. Okay? That's where they all come from. But the Kirchhoff's circuit law is obtained, of course, with the Faraday's law for closed circuits. That is a circuit that is closed. So we are using closed line integrals and the likes. But once you have that in mind, you'll always find that the two laws are the same. So since we are silent, then I'll stop the lesson and let's meet then next week.
A good day. Thank you.
Okay, nice weekend.